Hi, welcome to chapter number 21 and the last chapter of Chem 211. My name is Ramon Rios. I am professor in organic chemistry, and this is a recorded lecture to facilitate your study. Remember that in any case, this recorded lecture is in substitution of the attendance of a lecture room, in the lecture room, because in Khalifa University, the attendance to the lectures is mandatory. Okay, what we will do in this chapter, basically, we will talk about carboxylic acid derivative, nucleophilic acyl substitution reactions. We will talk about the naming of carboxylic acid derivative and the nucleophilic acyl substitution reactions. Okay, basically, a carboxylic acid derivative is a compound that contains this formula. A carbon double bond oxygen with another electronegative atom attached to this. In the case of a carboxylic acid, this is a OH, but for example, if we put a halogen here, we get an acid halide. If we put here another acid, we have an acid anhydride. If we put an alcohol, it's an ester. If we put an amine, it's an amide. And we put a thiol, will be a thioester. If we put a phosphate, will be an acyl phosphate. Okay, that means that there are a lot of different carboxylic acid derivatives. We will only talk about the most important. One of the most important is the acid halide, as you can see here. Okay, how we name this compound? Basically, we name this compound by taking the chain with the major number of carbons that contains the major number of acid halides, okay? And we name, for example, this one will be ethan, okay? It's the name of the major chain, that is 2 carbons. And then we put ethan oil, we add oil, and the name of the halogen that is in the formula. For example, here will be ethanoyl chloride. Okay, clearly has a common name that is acetyl chloride, but the UPAC name will be ethanoyl chloride. Okay, if we have the acid chloride attached to a ring directly, the name will be, we will name the cycle, and then we will put carbonyl chloride or carbonyl, the name of the halogen that we are using, chloride, bromide, fluoride, or iodide. Okay? In all the other things will be exactly the same way of nomenclature that we use it for carboxylic acids, aldehydes, etc. Esters, how we name the esters? The nomenclature of the esters is somehow quite similar to the ethers. What we will do is divide the esters into parts. One part that is after the carbon-oxygen single bond, that is this part, and before the carbon-oxygen single bond. Okay? The first part, this part here, the part that is before the carbon-oxygen single bond, okay? We will check the major chain that contains the major number of carboxyl groups, okay, and we will name normal. For example, this is 2 will be ethan, and we add 8. For example, this will be ethan no ate. Okay, for example, propan ate, hexanate. Okay, right? And then the second part, we will name the second part like a substituent. That means that this will be, this is an ethyl, because it's a substituent, we have to add the final -il, ethyl, ethanate. Okay? For example, here we have this part that will be termination -il because it's a substituent, terbutyl, and this will be a cyclohexane carboxylate. That means that the name will be terbutyl cyclohexane carboxylate. Okay? When it's directly attached to a ring, we will say, instead of carbaldehyde, that is what we use in the case of the aldehyde, in this case we will say carboxylate. Amides, how we call it amides? Again, with amides we do exactly the same than with the ester. We separate before the carbon-nitrogen single bond and after the carbon-nitrogen single bond. Before, we will say the name of the major chain that contains the major number of amides. For example, here we have hexane, because are 6 carbons. We will say hexane and the termination will be amide, hexane amide. If we have the amide directly attached to a ring, will be the name of the ring, cyclopentane, and then we will add carboxamide. Okay, and then we have to name the substituent, the compounds that are after the nitrogen carbon single bond, this one or this one, we have to name like substituents. In this case will be 1,2,3, propanamide, and this will be a methyl. Because it's an amide, we will say N-methyl propanamide, as you can see here. The hydrogen, we don't say anything. It's not named the hydrogen. If we have two different substituents, this will be, for example, this is a amide directly attached to a cyclohexane. That means that the name will be cyclohexane carboxamide. Okay? And then we say N-ethyl, because we have two ethyls, will be N-diethyl cyclohexane carboxamide, as you can see here. If instead of two ethyls we have a ethyl and a methyl, will be N-ethyl, N-methyl cyclohexane carboxamide. Okay? Good, then we can talk about the nucleophilic allylic substitution. Basically, the reactivity is very similar to what we saw until now. Okay, this is the compound, this is the functional group. Because O and X are two electronegative atoms, we will have a density positive charge over the carbon and a density negative charge here and here. Then a nucleophile, that is a friend of positive charge, will attack this carbon. The nucleophile attacks this carbon, and in order to avoid to break the octet, the pair of electrons that are forming the carbon-oxygen double bond are going to the oxygen. This is called a phase of addition. We add the nucleophile and we put the two electrons of the carbon double bond oxygen to the oxygen. Here you can see. We are forming a tetrahedral intermediate. Okay? Sorry, we are forming a tetrahedral intermediate. Now what is happening? Well, now what is happening is that, next step, we regenerate the double bond between the oxygen and the carbon, and the leaving group, X, is leaving, or Y in the slide, is departing. And what we have is the final ketone plus the leaving group. Okay? That means the process with carboxylic acid derivative will always be addition, tetrahedral intermediate, elimination. Okay, for example, we can do this exercise. We have this compound, and we add a methoxide. The methoxide is a nucleophile. The pair of electrons of the oxygen will attack the carbonyl group, the carboxyl group, and the pair of electrons that are forming the carbon double bond oxygen will go to the oxygen to form this tetrahedral intermediate. Okay, don't forget the charges. Once we have this, basically what we do is we regenerate the carbon-oxygen double bond, and the leaving group is departing. And what we generate is, in this case, this ester. Okay? Addition, tetrahedral intermediate, elimination. We can do several reactions of this addition, tetrahedral intermediate, and elimination depending on the nucleophile. For example, hydrolysis when we are using water as a nucleophile, alcoholysis when we are using an alcohol, aminolysis when we are doing an amine, reduction if we are using a hydride, or a Grignard reaction when we are using a carbon negative that is organometallic. For example, if we are using CH3-. Okay? The reaction will be exactly the same than before. We have here the acyl chloride, addition, tetrahedral intermediate, and then elimination to generate the ketone and the leaving group. Okay? Please do the following exercise, are very easy, try to do it by yourself, and if you have any question, please send me an email and I will try to answer any question that you have. Okay, and that's all for this chapter. Thank you very much. Remember to do the 3 questions, questions 1, 3, 5, 6, 7, and 31, and read the textbook chapter 21, points 1 and 2. And that's all. Thank you very much for your attendance, and with this we conclude Chem 211. Good luck in the exam, study, and be happy.